Hi, good morning, everyone. I am Renzhen Ling. I will lead the panel discussion for this morning. And for this morning, our topic for the panel discussion will be the pattern effect in projected long-term warming. And we have 5 presenters for this panel discussion on my left. Emily Newsom from New York University, Jiangsu Farm. Oh, Jiangsu Farm Enkar, Jonah Block Johnson from University of Reading, and Jennifer Kay from CU Boulder. And we also have Tim Andrews from Met Office Harley Center. He's online. And we will first go, the 5 presenters will present, I will talk a little bit on this topic, and then we hope to discuss with the audience. Either there's a Q&A or there's a comment, we're happy to take that. So I think we can start panel discussion.
Okay, so I just want to kick off this discussion by talking about where we may think the pattern effect may go in the near future. I think we've got a good handle on how the feedbacks now depend on a given SST change. So the kind of in the middle panel there, how the feedback varies over the 20th century. We've got all this kind of east-west specific ideas, the SST hash kind of metrics from Stefan's great paper. So the question really becomes, or where we might expect this to go beyond the end of this graph, is how do we expect the pattern on the left-hand side, so this feeds back into yesterday's discussion, what causes those, what are the mechanisms which cause that, and how might that pattern then evolve in the future, because each different hypothesis implies different futures for the pattern effect. So can we go to the next slide, please? I've got a non-exhaustive list of hypotheses, and I'm sure the answer is a bit of all of these. So they're not exclusive either. So the first idea is that this pattern of strong kind of East Pacific cooling, Southern Ocean cooling, West Pacific warming, which gives rise to the large pattern effect, is that it's natural variability. It just represent a mode of the Pacific Decadal Oscillation, ENSO, La Niñas, and there's certainly some papers that make this argument by comparing to large ensembles of AOGCM simulations. I think these are now called SMILES, are they, in CMIP 6? And it's certainly true that some members can kind of capture this pattern. But the problem for the attribution of that is that it's very, very rare, and most models cannot simulate this. There tends to be a bias. So the question becomes, are AOGCMs biased in their simulation of natural variability, or were we just desperately unlucky, as in the Fugger-Staller paper, that this peculiar pattern, as it were, was just extremely rare, and we don't expect it to be simulated often by models. But the outlook for that hypothesis would be, if we think this is just an extreme case, then perhaps the pattern effect is peaked, and I'll come on to this in the next slide in a minute, and then it may wane in the future. And then if it starts waning, what does that mean? Could we have accelerated warming trends? Unless that's buffered by ocean heat update changes, and I think Emily will discuss a little bit more on that. So the next hypothesis is forcings. There's a few papers which point to aerosols having a fingerprint in the Pacific SSTs, specifically on the PDO pattern. So I guess over this period, we're not talking about global mean because that's quite constant. It's more the kind of regional dimming continuing in Asia and brightening, for example, over North Americas. So the outlook for that, I don't know, but maybe this pattern effect may decline in line with a reduction in aerosols in the future, if we think it's partly that. The next one is volcanism. So Jonathan put forward a nice hypothesis in his 2020 paper that the decadal swings were associated with periods of volcanism or not. He showed that with AOGCMs that they can capture this pattern, but with the wrong magnitude. But we certainly would expect volcanoes to continue in the future, so maybe these decadal swings will just continue onwards. There's the thermostat mechanism, which Ule yesterday showed, and it gets to kind of Richard Seeger's work. going all the way back to the Clement et al. 93 paper. And that basically is just saying that we expect delayed warming in the Eastern Pacific because of cold unperturbed waters from below. So I think this is just a transient effect, not for ECS, where we expect those perturbed waters to eventually have been warmed. But this could, I don't know, just to throw out there, maybe we might expect the pattern effect to wane steadily throughout the 21st century as the deeper waters warm. And finally, there's some teleconnections. This is the one I know perhaps least about. I think Kyle actually wrote this paragraph, which I paraphrased for our manuscript, relating to the Atlantic Ocean, so the AMOC, and then the Southern Ocean, which was talked about yesterday. So if the Southern Ocean cooling is associated with this, then it could change if it's variability or if it takes centuries due to freshwater inputs, and we're talking much longer timescales. Okay, my final slide, if we can just move on. So very quickly, because I'm running out of time, I suppose. I just wanted to make, just for discussion, that are we already at the critical point, or has the pattern effect already peaked? So this gets back to Norman's question. So in the middle there is an estimate of the observed feedback parameter, which is the red on the kind of decadal variability. So that's from deep sea series and wide field of view stitch, top of atmosphere flux minus AR6 rates of forcing and Hadj Crew T5 temperatures from 1985 to 2014. And we get a feedback parameter of -2, which is in very good agreement with the atmospheric models forced by the observed SSTs and sea ice. But when we, unfortunately, the model stopped at 2014, as Norman described, which is unfortunate because we missed the big El Nino event. And if we include the data, the red points in there, when you get a large East Pacific warming, which is kind of shown in the bottom right panel, then the feedback parameter drops from -2 to -1.5. So that's the second red bar on the top left plot. So you can see that the already looks like this panel may be starting to tick upwards. So just leaving it out there as a discussion point. Could this just be a few anomalous years and it go back down, or are we starting to see a new trend? So all eyes on the next data of the tropical Pacific SSTs and the Earth radiation budget. And that's all I want to say. Thanks.
I guess that's me. That's a picture of the Enkar Hill where you're going to go hiking later today. And I thought after we had some introduction and wonderful comments from Tim about all these diverse hypotheses, you might just want to look at a pretty picture and let it sink in for a second. There's a lot going on here. It's the 8 a.m. session, so we'll keep it going, but also we're really looking forward to your questions and comments too. Next slide. So this has been a really, really fun workshop, and I'd say some notes that I really want to say is just follow up for it and really enable people to move forward with things. There's a lot of ideas here, and just keep in touch. It's really nice and privileged to be in person and online and interacting. For me personally, I have a computing grant that expires in August, and I've been doing a lot of cloud blocking, which has been super, super fun. I really like that framework because clouds are such a large source of uncertainty in many of these things, and the cloud aerosol interactions too. You know, if you're talking about aerosols, oftentimes the larger impact on radiative fluxes is through clouds. So I like it because it's causal and it's fully coupled. And we haven't heard a lot about it at this meeting, and there's a lot of techniques out there we haven't heard a lot about. There's been a lot of discussion about Green's functions, and that made me think about some of the history of kernels, and like when radiative kernels first came on the scene for calculating feedbacks in the climate system, there was like one kernel and everyone used it. And then a whole bunch of radiative kernels were made, and we learned a lot from them. And we kind of know, you know, the big picture things don't change too much, but there's details, model to model. You can make an observational kernel. And I can kind of see that happening with the Green's function right now. So I think that's exciting, but it's also really important to just remember there's a lot of tools out there. They all have their limitations, and this is just one tool that's kind of coming on the scene right now. So keep that in mind. I know there's a lot of early career people here. You know, the future is bright. There's a lot of different things that you can bring to bear on this. Coming right back to teleconnections, which Tim mentioned, I'll just put in a quick plug for a paper that I'm a co-author on, but used cloud locking to lock the clouds in the subtropics off the coast of South America in this region we've all been talking about. And it's really instructive to see that the models really differ a lot in their feedback there, and that when you lock the clouds there, you change the strength of the teleconnection from the southern hemisphere to the tropics. So again, just it's really important to have these kind of frameworks and lots of different ones to look at things. So that's all I have. I'm keeping it a little short since we have 5 of us on this panel today. So yep, that's it.
Hello, everyone. I'm Jiang Zhu, a project scientist at the Paleo and Polar Climate Section at NCAR. So I want to thank the organizers for putting me on this panel list. And it also made me very nervous because I have never done work on the pattern effect. But I did do some work on the state dependence of the cloud feedback and also in the paleoclimate. So here, my first question is very straightforward. It has been brought up in the past 2 days by multiple people. And the idea is how can we quantify and perhaps build a uniform framework to consider the state dependence and the pattern effect at the same time. So here, I'm plotting the zonal mean shortwave cloud feedback in very simple perturbed SST simulations. So here I apply uniform warming or cooling everywhere. It's very simple to do. So blue is you add a 4-degree cooling, and the green you have a 4-degree warming, then 8 and 12. You may wonder why I do this, because I think those are the simplest paleoclimate simulation you can do. For this SST minus 4K, it can be as thought as a 0th order of the LGM simulation, which is a cold climate. And for the plus 12K, it's sort of comparable perhaps to the Eocene simulation. You have a huge warming. And here you can see that in terms of the global mean, it depends on the uniform warming or cooling you add. And perhaps the order is the same as the pattern effect. And if you look at the different regime over the high latitudes, over the low latitudes, they differ a lot, which again, the difference could be on the order of 1 watts per meter square per K. And I think it's also perhaps on the order of the pattern effect. So I think it will be really interesting. We can build a uniform, unified framework to consider the two at the same time. Second question is about the two-way interaction between clouds and SST. This has already been brought up again. And here is a plot from the Alfani and Burrows 2019. The left is the zonal temperature gradient, and there are multiple simulations you can see. And the blue, basically you try to scale the cloud feedback in the simulation. And the idea is that if you artificially change the cloud feedback, you may end up with a different SST pattern. So I think in the past 2 days, it's really sobering for me to say that the current models may have difficulties in reproducing a lot of the SST pattern. I think it's and also it's really eye-opening to say that people use a lot of Green's function method trying to quantify the pattern effect. So here, this question is basically reverse to the Green's function approach. So suggesting that maybe we can target the important SST patterns through changing the cloud feedback, either artificially amplifying it or weaken the cloud feedback. Like Jen-K mentioned, we can do these cloud locking experiments and to see whether we can produce the SST pattern better. I'm not saying that every answer lies in the cloud, but given that the clouds are the most uncertain aspect in the coupled model, perhaps it's worth trying. Hopefully, we can get something different from this different view. Thank you.
Thank you, Jiang. Hi, everyone. I wanted to show you something that's maybe actually a little bit of an attempt to start to answer that first question of, are there ways of thinking about both the pattern effect and state dependence at the same time in a model? So this is a Gregory plot of CAD-CM3 under 3 subsequent doublings of CO2. You can see that the first doubling, that kind of looks a little bit like some of the plots that you might be familiar with of abrupt forcing, where it's mostly linear, but maybe there's a slight kink or change in the slope at some point, reflective of a pattern effect. Under 3 doublings, you see something that looks very much like state dependence, or in this case, it's actually runaway warming. So is it possible to have one framework that would address all of these different states? We've talked about Green's functions at this workshop. Next slide, please. Green's functions at this workshop, so this is the Green's function constructed for CAD-CM3. On the left. On the right, you can see a map of vertical velocity at 750 hectopascals. There's some slight similarities to these two figures, in the sense that the areas that have the strongest negative feedback tend to be the areas that have tropical convection. But there's some differences. Some of these differences are simply a result of the patch setup, the fact that there are somewhat large overlapping patches that tend to smooth out this picture. So next slide, please. This is an attempt to create a Jacobian where, instead of using large patches, these are sort of discrete, small patches that have quite thin differences in latitude. So maybe trying to get a little bit closer to this map. So it's still not exactly the same. There's still some differences, but this kind of gives an idea that maybe first order, it's possible to divide up the world between tropical convecting regions and elsewhere. So that would allow us to use sort of like a 2-region model, somewhat inspired by Dong et al., which breaks up the world into the West Pacific warm pool and everywhere else. Next slide, please. So as a possible way of reconciling these two nonlinearities, what I've done here is run a series of fixed SST experiments with these 2 different regions, both in isolation, but then also jointly. So that this way, and done this at a number of temperature levels, so this way we can get both the temperature dependence associated with each of these regions, and also the cross terms that emerge from warming in the regions jointly. So next slide, please. So I've done this at 3 different CO2 levels, and you get this sort of grid of values of n associated with the different CO2 levels and the different warming in these 2 different regions. Next slide, please. If you simply interpolate between these regions, you get this very complicated looking, this isn't quadratic, this is something really kind of out there looking and wild. They're actually mostly the same as each other, but sort of offset by a forcing term that's pretty constant. So if we were to assume that warming followed just a perfectly uniform pattern, the warming in the 2 regions happened at the same, had the same amount of warming in each region. Next slide, please. You would not be able to recreate the full response. You'd get some slight positive temperature dependence, a slight slope, but you would not get the full behavior of the model. If you actually use the warming patterns in these 2 different regions, next slide, please, you are able to get both get the pattern effect that happens under low forcing, and also this sort of very state-dependent behavior that happens at higher forcings. And part of that higher order behavior has to do with a pattern that then interacts with the state dependence. So it's just to say that maybe something like this, a 2-region model, with cross terms could be a way to start to think about reconciling these two different aspects of changes and feedbacks. Just one slide to show, this is important for thinking about paleoclimate, but it's also potentially important to think about some of the maybe some of the worst case scenarios involving anthropogenic climate change. Next slide. So this is some stuff that didn't make it into the feedback temperature dependence paper, but this is a attempt. We fit a number of these CMIP6 models where we had long-term warming trajectories, and we tended to see that the warming, the nonlinear terms did not matter much by 2100, but by 2300 they started to have some effects in these high forcing scenarios. So if we did a sort of Monte Carlo experiment of taking all of these different values of nonlinearity for these different models, and then creating an ensemble of potential future warming pathways. Next slide, please. And then we got distributions of potential warming in the future based on this. And our findings was that the nonlinearities did not affect things very much by 2100, but did have some effect, especially in the long tail by 2300. So it's, again, a way of saying that these feedback temperature dependence issues might start to become important in thinking about sort of the worst case down the line, even if it's not the most likely thing to happen or the most near-term thing to happen. And I don't think these slides made it into the things that were put online, but I just wanted to mention, and maybe I'll put it in the Slack, something to speak to some of the work that was done. I was thinking some questions that people had yesterday about thinking about the role of both ocean heat uptake at the same time as thinking about feedbacks in response to a given SST pattern, and also in shaping subsequent SST patterns. There's some interesting work by another postdoc in working with Jonathan Gregory Charan Wu, who's managed to create an approach in which he creates a matrix that kind of summarizes both the atmosphere and ocean responses, and then uses that to propagate various patterns of warming forward. I just think that it's an interesting road to try to get this Green's function idea and apply it to the full coupled system. Of course, I think Malta also is mentioning some approaches along these lines, but I'll try to put that in the Slack. Oh, it did make it in. Well, okay, so this is the word. I just talked about it though, but yeah, I'll let Emily go.
Well, actually, this is quite related to what Jonah was just talking about. I'm just going to take this opportunity to list some questions that I had, less things that I have to say definitively about the pattern effect. But something, as Jonah was just saying, that I also think came up yesterday, been on my mind, is what the relationship is between ocean heat uptake, radiative feedbacks, and the pattern effect. Just to illustrate this relationship, this is in CMIP6 on the right. This is the correlation between lambda and ocean heat uptake normalized by the forcing across these different SSP scenarios. And as you can see, there's quite a strong anti-correlation between these two. So models that have stronger feedbacks tend to take up less heat into the ocean. This has been found before by others. And while I think you can partially explain this just by the relationship between both lambda and ocean heat uptake and global mean temperature, kind of where lambda leads to a smaller global mean temperature, or a stronger lambda might lead to a smaller global mean temperature, which might lead to less ocean heat uptake. I think that doesn't really explain all of this correlation. I think Jonathan and others have shown that ocean heat uptake is not fully linked to global mean surface temperature. So a question might be, do models that tend to have greater ocean heat uptake also tend to create SST patterns that weaken global feedbacks, or kind of vice versa? I call this question 1.5 because I think it's quite related, but another thing that has come up that I find really interesting is what is the relationship between AMOC and other aspects of the ocean's background state and radiative feedbacks and perhaps the pattern effect. This on the top, thanks to Jonah for sharing this with me. This is some work from Jonathan Gregory and co-authors paper that Jonathan talked about, I think, yesterday. And what they're showing on the left is the relationship between lambda on the y-axis and AMOC, and you see that there is some correlation between those two. And on the right is the pattern correlation of SST change and the strength of AMOC, showing that there is actually a characteristic pattern of models that warm in a certain pattern depending on the strength of their radiative, or sorry, their AMOC. And then also something super interesting is your work that we heard a little bit about, which is showing the relationship between the change in the AMOC between an early and late period and the change in the radiative feedback parameters, so the pattern effect. So that's really interesting too. I just want to make the point that when we talk about the AMOC, we're not necessarily, or when you link something to the AMOC, there's other things in the ocean state that are also quite correlated to the AMOC. This has been shown in nice kind of simple ways by John Marshall and Oleg Senko. On the right is the relationship between the overturning stream function in the North Atlantic and the depth of kind of the characteristics mid-latitude stratification. Kind of the inverse of that is something I'm showing, which is just the average n squared or stratification in 400 to 1200 meters across different CMIP6 models and the AMOC. And so to rephrase my question, it's kind of how is the AMOC related to feedbacks and the pattern effect, but what really matters? Is it the pre-industrial AMOC strength? Is it the change in the AMOC? Or is it other aspects of the ocean's background state that correlate to the AMOC? I think there's a lot left to understand here. And also something that's come up is what is the best framework for studying this ocean feedback kind of coupling. Talked about coupling an ocean Green's function to an atmospheric Green function, but I think work like, for instance, Yemi's work has shown that the dynamic ocean is really important to getting SST patterns correct. There's also other things, observations, but also Dave Bonin is working on this cool MEBM coupled to a simple ocean model. That's just something I'd like to discuss more. And then final question, kind of a different thing is, I'm sure someone's thought about this, but we haven't heard much about it. We tend to see a lot about 4 times CO2 experiments. I'm curious, how much does the forcing history affect the pattern effect? So what I've shown here on the left is the change in SST at year around 2300. This is in CAN ESM5, just to show you. So on the left is the difference in the temperature anomaly between 8.5 and 2.6 SSP. And on the right is the same pattern, just normalized by its global mean. And as you can see, not only is the climate a lot warmer, but the actual pattern of long-term warming is quite different between these two scenarios. And so that would, that's just something to maybe keep in mind or discuss in our group. So yeah, that's okay. So many thanks to our 5 panelists for their great talk. And we will first start with asking if our 5 panelists have questions for each other, comments, conflicts.
I was curious if some of the cloud locking techniques could be used to help answer Jiang's second question that he brought up.
Yeah, I think it's just great to think about all these different frameworks. And one of the things that came out in our breakout session was actually the same idea that John said, which is like, can we turn up and down the cloud feedback to change the spatial pattern? Like cloud locking is just removing it, which I think is, but there's also, I think, some potential to turn it up or down. And I don't know, I think there's more to do in that framework. I also just want to put a plug that it's not so easy to do either. like the Green's functions are really nice because you don't need to rerun a couple models. So I appreciate that it's harder, but it is doable, and we've seen it in several models, and I think it could be fun to probe the system, poke the beast in a different way.
Great. And so we are open to the audience in the room and also online participants to join the discussion, and feel free to raise any questions in your mind, any comments. Hey.
Well, there's some questions on Slack and WebEx. So from WebEx, Masa asks, well, this comment, Tim Andrews, the extensions of AMIP PI forcing is really interesting. I don't know if...
Yeah, well, there wasn't actually an extension of the simulations in there. It was the most recent observational data which was suggesting this big change. It's just really unfortunate that the protocol finished at 2016. So we could maybe look at the 2014, sorry, the runs that we did for Norman for the Lobatar, where we extended the AMIPs. But it's a bit of a mix of, it's not quite perfect AMIP PI forcing. Some had changing forcing age. So if anyone's interested in another intercomparison, we should be extending our AMIPs, I think, all the way right up to the most recent data sets to see if the models capture this big radiative effect in the most recent decades. So I agree, Masa.
Maybe I'll follow up on that. It seems like a huge loss that the AMIP and AMIP PI forcing protocols are always 6 years or 7 years behind series, especially since a lot of the interesting stuff in series seems to be happening post 2014. Because of the way the CMIP protocols run, this is probably going to be the case for CMIP 7 as well, unless we make a decision that we're going to keep the AMIPs sort of up to date.
It's more, I think, from a technical perspective, it's you've got to have people that develop the data sets for all the boundary conditions and keep them up to date with aerosol emissions, the SSTs, the CIs, and then the modelers have then got to turn them into boundary conditions for their model. So it's actually not quite a trivial job as it sounds, just to extend your AMIP. So there are reasons, but I agree 4 or 5 years is a bit out of date.
Hi, Robin Gamgatel from Lagos. So I was just wondering about the plot we're having on screen now. So maybe there's something I misunderstood here. Are they normalized by the mean temperature before doing the difference or not?
Let's see. I did this very late last night. No, basically I took the left plot and I normalized by the global mean of the left plot.
But if the 8.5 is has the same pattern but with a stronger magnitude, if you make the difference, well, you will see a difference even if it's the same pattern. So I feel you might get different results if you normalize before doing the difference.
Yeah, you're right. I guess what this is showing us is these are the places where 8.5 will, even if they have the same pattern.
Well, I thought your point was to say that they had a different pattern.
I guess my point is the difference is not uniform between, let's see, I have to think about this. That was my point. Maybe this isn't a good way to show it.
All
yeah.
Right. Well, thanks.
Can I make some follow-up on that point? Oh, actually, I mean, I quite like the point, the figure you showed, like, because we also looked at the relative SST warming pattern at the end of the 21st century between high forcing scenario, for example, RCP 8.5 versus two forcing scenario as RCP 2.6. And we do like the normalization, normalized by global mean, and just show the relative warming pattern. And indeed, I think this model is not unique. We found this difference in the tropical West-East gradient or Southern Ocean, actually pretty apparent in all of the simplified models. So, the interpretation we had is that it's not only cares about your forcing, like how much aerosol or CO2 greenhouse gases that you change. It also relates to the forcing time scale. It's like high forcing scenario, basically like just the constant forcing goes up throughout the whole 21st century. So like 1% transient forcing. Well, for low forcing scenario, we added into CMIP archive. It's more like you peak at the end of a century, in the middle of a century, and then get us closer to equilibrium in the middle of a century. So it's almost like transient versus equilibrium type of a difference. So it's worth to think about how the pattern effect, what kind of a role the pattern effect plays into transient warming pattern, the transient global warming rate.
Yeah.
Out of like 21st century. Yeah. I think
makes
this
a
is a
lot of
really great
sense.
point. And we had this project looking at all of the simplified models, but never finished it up.
Yeah. And maybe also just the relative impact of kind of recalcitrant deep ocean warming
Yeah,
might be more if you have a lower global mean surface temperature anomaly by the end of.
and a more
That's-
realistic, but also transient timescales.
Yeah, we have online questions from.
Ben Sanderson has his hand up.
Yeah, hi. Yeah, nice discussion, everyone. So I guess a couple of questions which are tied together. Like, firstly, in Tim's original talk, you said something along the lines of you'd expect to see the pattern effect decline over the course of the century. And it relates to the plots which is on the screen, and the last comment in that. I guess my baseline expectation is that in this transient, this linearly increasing forcing regime, we'd expect to see the same pattern just linearly ramping over time. But then as the forcing stabilizes, you'll see sort of a saturation of the fast timescales, and then the slow timescales will keep on responding, and then we start seeing the pattern effect. So, and then we start seeing, big changes in the warming pattern. So I guess I'd like to know a little bit more about why do you think that the pattern effect will decline irrespective, even in a high forcing scenario? That's my question, I guess.
I guess that one's for me. It's a good point, and I think it would. It kind of just goes back to all those points I made, though, and depends what you think is causing that mechanism. If you think it's variability, then sure, it will just keep going on and on and on, and I'd expect it to wiggle around, and maybe as the forced pattern emerges amongst that, over that, gets stronger, you may see it decline. But yeah, I take your point. One thing I couldn't think of, and maybe slightly different, ask a question slightly different to your question, is I couldn't think of a mechanism which would make the pattern effect get stronger from this point. So on that basis, I kind of was thinking, well, it kind of has to decline. So I don't know if anyone can think of something. What could make this gradient or warm pool warming relative to tropical mean, or however we want to phrase it, or southern ocean cooling, more extreme than it is today going forward? And presumably we don't expect it just to stay constant. So on that, I kind of just had the idea is that this is going to wane. Guess that was I don't know the answer, but that's kind of where my gut feel was going.
I guess the counter to that is like there's more than one pattern effect, right? There's more than one pattern which is being manifested here, and so if there's a deep ocean warming pattern which is going to be manifested over long time scales, and that's a force response, then we would expect that to be more represented as forcing stabilizes. But if there's variability source patterns, then you might expect them to decline as the ratio of force to variable force change to variability declines over time.
So, and we expect that long time scale response, though, to increase the pattern effect as well, or reduce, depends which way you define it. Reduce the difference from where we are today to what we expect in the future. From the AOGCMs, depending how you phrase it.
Let's talk about that later.
Okay.
Okay. Thanks. Kyle, please take away.
That's a really good question, Tim, about what could potentially cause this to become a more substantial pattern effect. I can only think of one mechanism off the top of my head, which would be Antarctic meltwater forcing. So Yue Dong has a great poster on this, and Shania Sadai, I believe her name is, has a great paper showing that if you add a bunch of freshwater forcing over the 21st century, you can get extreme Southern Ocean cooling extending into the tropics. If that is already happening in nature and it accelerates, you can imagine this getting more substantial. I don't know if that's the right mechanism or not, but that's possible. But I just want to point out, just to connect the dots on this figure, this is really cool, Emily. Looking at this pattern, I think what this is saying is basically when you start to ramp down your forcing, you get a more polar amplified, you get a more equilibrium-like pattern out, right? Because you get closer to equilibrium. There's a couple papers on climate commitment that I think address this. Thomas Froelicher has a paper from 2014, I think, and then there's a new one who I apologize, I forget who first author was. It might have been Chen. I think Mark is on this paper, showing that the pattern effect basically gives you climate commitment. When you reduce your CO2 emissions, it doesn't necessarily stop the warming like we think. You can imagine ongoing warming because you get closer to equilibrium when you reduce your emissions. And so the pattern effect actually has implications for things like carbon budgets. That if the pattern effect is substantial today and it goes away when you shut off your emissions, you get a more polar amplified pattern with more warming in the East Pacific. This has major implications for how we think about future warming, even as we get to zero CO2 emissions. So that's just, I think, a somewhat unexplored, only 2 papers I know of, but it's this pattern that does that, I think. So thanks for showing this.
Can I just add on there?
Yeah.
Or is there someone online?
Yeah, please.
Yeah,
take
so just because it's directly following up on that question of what could strengthen the gradient going forward, I like to think about the meridional gradient. So if you did have a mechanism that could increase your subtropical to deep tropical, your mid-latitude to deep tropical gradient, so adding on to the meltwater comment, you know, if there was a cloud feedback mechanism that would actually act, and I'm not saying that there is, but something that would act to strengthen the meridional gradient, that would then map to the zonal gradient in an equilibrium scenario, right? So something to just keep in mind mechanistically that's something that could give you an equilibrium response that's more of a, you know, stronger gradient response.
I just want to comment quickly about the meltwater because this is not a new topic. There's been actually a lot of work done on it and very different answers in different models depending on the mean state of the Southern Ocean, which is also a region that has, you know, large differences in stratification. And so what happens to that meltwater when it goes into the Southern Ocean and how big of a flux you need? It's a really model dependent question. I don't know, Andrew wants to say anything about this. I know he's worked on this, but yeah, it's a big question. I agree it could help in strengthening this pattern, but it's not a simple thing to answer.
Yeah, just to follow up Jen K's question and to combine with what Jonathan Gregory told us, it seems like mean state Southern Ocean and mean state AMOC both also have impacts on how the heat uptake being mixed to the ocean, and in that way to modify SST. And so just raise a question about the mean state Southern Ocean and mean state AMOC. Is there any relationship? I open this question to everyone. Yeah.
That was my question. Yeah. I think there's a lot to look at there.
We have online questions.
Yep, an online question from Marianne. Go ahead.
Yeah, hey, this is not super new now from the discussion that's already been had, but I was just going to say something along similar lines as what has just been said about the ocean circulation, basically how fast the ocean responds in the SSP 126 versus the SSP 585. Because of the different strength of the forcing could really have an impact on those, how different those patterns are, especially in the Atlantic Ocean, I think. So that was just my intuitive, this was my first thought to seeing this plot. But I think, yeah, a lot of this has already been kind of said now. And the other thing that I was wondering how potentially aerosol, changes in aerosol forcing could maybe lead to a strengthening rather than a weakening of the pattern, but I'm not really sure where the aerosols would have to change in which way for that to happen, but I think that could potentially have an impact.
Any ideas about? If not, I saw comments from Gregory. Isn't that Christy?
He just says there's probably a relationship between the mean states of AMOC and the Southern Ocean related to stratification. So kind of echoing some of the things that we've talked about.
Thank you for. So I think we
So
can go
can I
on.
just chip in on the Southern Ocean question? I was just thinking, we tend to always define our pattern effects to, we make an assumption that the AOGCM long-term patterns are correct. We question this a little bit, but that's generally how we define it. For example, 4CO2 AOGCMs, lambdas. But this Southern, I've not really thought about this, so I'm just kind of thinking aloud. But the Southern Ocean meltwater has quite important implications because I guess our AOGCMs don't include that process, right? We don't have interactive ice sheets. So is this an area where we could be making an argument that our projections of the Southern Ocean are incorrect in this respect? I've got no idea how important this effect is.
My understanding is the jury is kind of out for how important that signal is, the meltwater signal. But maybe Andrew can comment. He's working on this.
Yeah, I think it's wildly model dependent at the moment, as Jen kind of said. So depending on which model you do this meltwater experiment in, you get a very different answer. Like by a factor of 10 for the amount of meltwater that you put in, you get the same effect. So there's an upcoming freshwater forcing MIP that should help answer this, where a bunch of different models are being run with the standardized freshwater forcing. So maybe we'll get an answer soon, hopefully, yeah.
Thanks. We'll go by
Sally Zhang from Johns Hopkins, related to the Southern Ocean and also the point that Tim showed about the teleconnection. I guess maybe just to clarify also my pacemaker work that I showed a bit yesterday. So if we just look at the observed trends since 1980, and if we apply that cooling over the Southern Ocean, at least in CSM1, in a fully coupled model, actually the response in the tropical Eastern Pacific is really weak. So it's not statistically significant, even after you run 20 ensemble members. And so I guess my point is that the observed Southern Ocean cooling effect on the tropical Eastern Pacific is definitely going to be masked out by the internal variability in that region. So I don't think, although like a lot of more idealized studies have shown an impact from the Southern Ocean to the tropical Eastern Pacific, I think if we're talking about the observed trends and the forcing magnitude with the observed trend, it's actually relatively weak.
Okay, we have online.
I think Sarah's gonna maybe answer this.
Oh yeah, I was gonna add to Sally's point. So I generally agree with Sally's comment that in CSM1, I think you see weak Southern Ocean impact on the Southeastern Pacific is because the cloud feedback is so weak in that model. So we actually, Sally, you know, that we did Southern Ocean pacemaker experiment with CSM2, and we actually find significant substantial cooling response in the Southeastern tropical Pacific in response to Southern Ocean. So I think that impact is going to be model dependent, and I think that the model dependence comes from the cloud feedback. Yeah.
Thanks, Sarah.
That's super interesting, Sarah, also in light of what Clara showed yesterday with the CMEP5 forcing in CESM2, that you can all of a sudden start to get that cooling in the Eastern tropical Pacific in a model where we never saw it before. So there's something different maybe with the cloud feedbacks that's helping explain why that we're seeing that response differ.
Christy.
So there's a question online from Gita. Emily, what's happening with the aerosol forcing after 2100 in these extended SSP simulations? At 2100, the aerosol forcing is really different between SSP 585 and SSP 126. Granted, the CO2 will swamp the global mean, but like someone said, it's the anomalies from the global mean that matter, and I wonder if the aerosol difference could play some role in the pattern difference. I need to make myself a shirt that just says aerosols in all caps.
I think that's a great question. I maybe regret making this plot because I don't know very much about these runs. It's just but I think it would be, maybe someone here knows more about this. I think that's a great point, not to forget about that. I don't know, but good point.
Okay. So I think Mate, do you want to take away?
Yeah, maybe just a short. It's a bit of a different aspect, but I think we should also be aware of, if we're interested in the future evolution of the Pacific warming pattern, actually a process that we haven't discussed in the plenary so far. A small plug for the poster that's one of my posters that's online, based on work by Michiya Hayashi, is that actually in the observations, a big part of like mean state change in the tropical Pacific actually can be due to ANSO variance rectifying on the mean state. All the CMIP models, nearly all of them, don't capture this process. 80% of them don't have this important nonlinearity. And therefore, there could be a strong control how, and if ANSO variance changes in the future, it would rectify on the mean state in the Pacific. And we don't know yet if ANSO variance will decrease or increase in the future. So that will also add to the uncertainty in the long-term trend. Maybe one reason to put additional uncertainty in the long-term projection in the tropical Pacific.
Yeah, I agree. So maybe Kyle.
I was hoping Tim could address something. I think yesterday, or maybe the day before, I've lost track, Peter Hybers was talking about uncertainties in the historical record, as was Chris Karnauskas, in terms of our inability to really understand what SST patterns look like in the past. I think that gets even worse when you think about sea ice. So Tim, I was wondering if you could just summarize for us our current thinking, or your current thinking, on how important those uncertainties are for quantifying the historical pattern effect. Do we have estimates of how bad that is on a range of timescales? How big of a problem are our data uncertainties to quantify this?
It's a great question. I've only dealt with 2 data sets so far, AMIP2 versus HADIS1, or HADIS 2.1. And it's true that you get, so I think there's a few papers have shown this, the Fugistella and Silvers, Lewis and Maritzen. You get a larger warm pool trend in the AMIP2 boundary condition data set, just the standard data set we use for our CMIP AMIP runs. And that does generate more negative feedbacks. And over the historical record as a whole, I think we found it's about 0.2 watts per meter squared per K difference in the pattern effect. And actually, it's quite coincidentally, or by construction perhaps, it's that difference. So for example, in the WGCM ECS assessment and AR6, they used a pattern effect of 0.5 plus or minus 0.5 watts per meter squared per K, which they based on my previous paper, which had about a 0.7 watts per meter squared per K pattern effect. And with a bit of expert judgment, we allowed for some of this. And when we've done the simulations now, we actually get pretty much exactly what we allowed for, which was quite relieving to to find when we ran the simulations. And Gushman has done a few more, and I think there was a strange Volcaro et al., which I don't know much about, data set. I think he's got a poster here which gives a smaller pattern effect. I'm not sure how plausible that data set is. You are right for sure to bring up sea ice. That basically just dominates everything. If you run an AMIP PI forcing simulation with sea ice reconstruction from HADIS 1 versus HADIS 2, you can change your feedback parameter by the size of the pattern effect. And this all just comes down to the fact that we do not know, and you can then trace it back down, and it basically comes down to small assumptions they made in the reconstruction of Antarctic sea ice in 1850, which we basically have no clue on. And that can change, but it's not so much. I mean, obviously, that's a really interesting question to understand and try and constrain sea ice feedbacks, but we can get around that for just looking at the SST kind of driven pattern effects. But it is a great question, and there's not much we can. Well, we do need to quantify it further across a range of data sets, I think, just to really nail that one.
I don't know if Clara Desser is online, but I know she's also done a lot of work trying to reconstruct SSTs and CIs like over longer timescales. But yeah, you might want to chat with her, Tim.
Okay, thanks.
Yeah, Christy.
Hello. Okay, less of a question and more of a ramble. There's this concept of Gelman amnesia. Like you're a climate scientist and you read the paper and you see an article on climate science and it's completely wrong, right? It says that warming causes increase in CO2. Then you flip the page and you read an article on the economy and you just trust it because you don't know anything about the economy and they're the newspaper and you forget that on the one thing that you do know something about, they got it completely wrong. Are we doing the same thing with the patterns? If we think that the models don't get the historical patterns right, and then we're spending all this time trying to understand what kind of biases might be. And then we look into the future patterns, and because we have no observations of the future, we kind of just take the model patterns as is. And this is something that concerns me, is how much can we trust the long-term pattern of warming from models? So to actually make a question, this more for Jiangzhu, if you look at the Pliocene and you look at abrupt CO2, then it sort of really matters whether you think the abrupt CO2 pattern is the future pattern, the Pliocene was doing something different because the boundary conditions were different, or if you think the Pliocene is actually what the future looks like. So I guess I said there's a ramble. The vague question is, how do we get better constraints on what the future pattern might look like? And it seems like the paleo record is really the only place to go to understand how reliable are long-term patterns in models.
Yeah, thank you. I appreciate this question. And I think, as you have mentioned, Pliocene might be the best place to go to in terms of comparing the long-term SST pattern. And unfortunately, I don't know much about Pliocene. I'm not sure whether Natalie has something to add. And I want to mention that we also have LGM. Maybe we can make some use of in terms of the SST pattern response to CO2. And the uncertainty, another uncertainty is for the glacial climate, we have the ice sheet forcing that can complicate the story.
Thanks. The only thing I would add to that is just the point that I was making in the presentation. So I think having robust reconstructions is the biggest challenge that we face, especially for the Pliocene, Miocene, to be able to robustly reconstruct the patterns, right? But I would say that everything from the paleoclimate in terms of the pattern effect does seem to be falling below the line of the 4 times CO2 run. At least that was for, in Vince's example, the CSM kind of 4 times CO2 abrupt pattern, right? So I do think the paleoclimate can at least hint to whether potentially the feedback parameter, which side the feedback parameter is falling on this line in that we have in our models, CMIP models, versus what we have in the paleoclimate. And I think for me, it's going to be looking across several paleoclimates to see if there's sort of a robust pattern effect that's coming across in multiple, Miocene, Pliocene, Eocene. And if they're consistently falling below the 4 times CO2 CMIP runs, then maybe we should be asking ourselves how much faith we're going to put into that, right?
Peter Hybers here. The discussion we had in our working group yesterday was that when we're kind of looking at the patterns, we tend to use the base state as something from the late 1800s relative to what we have today, but we really don't know that base state very well. And so the uncertainty in the patterns could have as much to do with kind of what we think the base state is. In fact, that's going to be much more uncertain than where we end up. And so I was wondering, if you want to see if you can predict patterns, it'd be nice if we use the modern as the base state that we're using as the reference. And then we'd like to predict something. And so going into the past makes sense. Paleoclimate past is difficult. But could you somehow initialize the model using the current base state and then run it backwards or run it towards trying to understand what the kind of late 1800s look like. And then with the sparse observations we have in the 1800s, make that comparison. I mean, what I'm looking for is, can we somehow use the instrumental record in a smarter way to initialize a period where we have more observations and then verify in a period where we have sparse observations but still have something?
Maria,
Say something on that?
yeah, sure, Tim.
Yeah, because I was going to bring this up a little bit because I saw on the Slack channel that we may have some people here that do kind of initialized simulations. It's not something I do, so I don't really know a great deal about them, but I think it's an excellent question, what we can learn from them. So you, and I know when I first started thinking about this and I wanted to know, well, what the questions I was asking, what are the SSTs going to look like in 5-10 years? In the Met Office, we've got our seasonal to decadal forecasting group, and they do exactly as was just described. They initialize from the present day SSTs and run them forward, and they go back and do hindcasts over the historical record. I was quite excited, thought that's brilliant. I'll just go and ask these guys, they'll know. And they pretty much just said to me, oh, we have zero skill in the tropical Pacific, which was, I don't know if I caught them on a bad day or whether they, were just completely interested in European weather at that particular time when I asked them. I don't know if it's maybe our model, but if the people that are chatting online about these kind of initialized forecasts can say something, that would be great. If we do have skill on the kind of 5 to 10 year timescale on tropical Pacific SSTs, I'd love to hear it.
I saw someone online.
Yeah, Michelle Leroux is before that. Michelle Leroux has made some interesting comments on Slack about initialized forecasts, so you should check them out. And then online, Marianne has her hand up.
Can I make a brief reply to Tim first?
Yeah, sure.
Just wanted to say that a lot of the initialized forecast community has been focused on predicting things you have some higher amount of skill for like a season or a year, and then you don't have skill more than a year or two out in the tropical Pacific. But if for the pattern effect you care about a decadal average, your skill time might be much longer. And so then you might have skill in the tropical Pacific if you care about a several decade average. And so there's been a group of us at NCAR that have been looking at the skill you get in decadal averages from the CSM2 initial, the CSM2 large ensemble, which has different ocean initial conditions, and finding that you have some skill some 50 years into the simulation. And it's a very, very small amount of skill compared to what you'd want for make a prediction that's societally relevant, but it may still be useful for the pattern effect. So there may be some reframing and meeting in between for these two communities to do to make progress in that.
Thanks.
Yeah. So.
Marianne?
Yeah, I just want to say something that might be a little bit controversial, or I don't know, but just regarding Christie's comment or question. I think that if you take a step back away from thinking about the pattern effect and how good models are at representing it and how good they may be in predicting future SST patterns, I wouldn't lose too much confidence in how good climate models are overall, because I think the thing that overall we as a society care about is predicting land changes, because that's where most of us are. And I think in that sense, I mean, obviously the pattern effect affects ECS and has knock-on effects to precipitation changes and everything. But I think the changes over land with warming and droughts and everything are probably reasonably robust, even if the models don't do such a good job at predicting or at capturing the historical SST patterns. Maybe I'm just opening a can of worms here. But this kind of comes from the discussion that we had this morning in the European breakout session, where we kind of went into a bit about how much the land is contributing to the pattern effect and stuff like that, where I just kind of thought, well, ultimately the thing that we care about is what happens over land, pretty much. Yeah, but maybe, yeah, this is maybe a bit off topic.
I disagree. To get the precipitation over California right, you need the SST pattern right. They're totally linked.
So I wanted to make a pitch on paleoclimate is great, and I actually care about the equilibrium, but what we actually care about is the next 50 years. So I think we need scenarios for, and Tim played this out a little bit, either we trust the models and we have to get from where we are current to the forced response we trust the models of, or we do not trust them, and we could come up with new SST pattern scenarios. And instead of looking in great detail into 20 different realization of SSP whatsoever, we could think of ways to what if the East Pacific changes its warming rate over the next 10 years, 20 years, 30 years, 50 years, we don't know. But we have more physical knowledge there. We can test different scenarios. This is why, and get independent of the coupling of the models, which we have good reasons to be critical about. Does this make sense? Go to Mark Alessi's poster who starts doing this.
Just to add to that point as well, it is a very good point, because whatever's going on with the recent pattern, it seems that the AOGCMs, unless it's an incredibly rare event, are biased in it and they struggle. They cannot do it. So it's very difficult to use them then to test the various hypotheses we've got forward if they're deficient in the thing we want to test. So kind of developing maybe physical based plausible projections independent of the AOGCMs based on understanding sound like quite a good idea.
We're coming on times. Michelle has had her hand up, so we'll take that as a final comment. Oh, sorry. Jonah wants to answer.
Can you hear me?
Yeah.
Yeah.
Okay. Yeah. I'm really just this meeting's fascinating. I really appreciate how much I've learned from everyone. I do want to kind of echo. I feel like I've said a lot on Slack, but the nice thing about initialized climate models is they give you instant feedback on how well the physical models are doing. You can compute error relative to the observations. And I realize that we're looking here at timescales that are well into the future, but if the goal is to try and figure out how reliable the models are, then I think you really need that kind of instant feedback. And I realize that initialized models kind of have, they're more challenging than free runs. I know that several centers in the past have had trouble with initialization shocks and so forth. But now with the NME, we have several model centers that do this very successfully, and initialization errors are not as much of a problem as one might think. So I really do advocate for this idea of having large ensembles that stem from initialized models, and they could be forced with various scenarios. And so you can see how well they're doing in real time and the biases that develop. To my knowledge, the only model that does this, the NME project, is GFDL SPEAR. This is something that we use as seasonal prediction, and they also have a large ensemble. But I think this is the only model. So it'd be great if there were more of these models stemming from these initialized, simulations. Anyway, that's all I wanted to say.
Thanks for the comments from Michelle, and too bad that we need to end here. And thank you so much for the online participants. And for the participants in this room, we can still talk a little bit more about this in our breakout session. So on the screen, you can see, Maria, if you want to talk about this.
So we have a few minutes of a break. We go right away to the breakouts. Okay, no break.
No,
Grab
you
your
have a few minutes, 5 minutes.
5-minute break. Go to your breakout room, and after the breakout, there will be poster session and lunch together. So we will reconvene here all together only at 1 for the last panel discussion.
Yep. And then the online folks, I will open up the one breakout room. Pierce is going to lead that one as well. And all of you guys should get a request to go into that breakout room. You just need to accept it.
Okay, make one pitch for the breakout rooms. So I think the discussion yesterday was great. Just in terms of the workshop, I think we should start thinking a little bit more towards how do we actually address these great questions we have now? Think about what would be the observations we need, what are the simulations we should run. Sorry, Christy disagrees.
Okay, good afternoon, everyone. Thank you for coming to the third panel discussion, Moving the Field Forward. Our panelists today are in person Mark Zelinka from the Lawrence Livermore National Laboratory and David Schneider from the University of Colorado. And online joining us is Piers Forster from the University of Leeds and Geeta Persad from the University of Texas at Austin. So we're going to go ahead and start with the panelists sharing a few slides to get us started with the discussion.
And Nader Jivanji from Princeton GFDO.
Oh, thank you. So I think up first is David.
Good afternoon, everyone. So previous panels set the bar really high for these presentations. So the best I could do was steal this schematic from Clara Desser, who had something similar yesterday, but instead of putting the pattern effect at the center of the universe, I put the Southern Ocean and Antarctica at the center of the universe. So see if the little clicks works. Okay. So the world kind of literally revolves around the Southern Ocean, or maybe it's more accurate to say the Southern Ocean revolves around the world, and it integrates climate signals from all the different ocean basins, and it, through the atmosphere, it communicates directly with the lower latitudes. So there's a lot of rich climate information that's integrated in the Southern Ocean. There's been a number of presentations at this workshop on how strongly the Southern Ocean is connected to the climate sensitivity. It's an integral part of the pattern effect. There are all these different processes: heat uptake, carbon uptake, cloud feedbacks. Some of my work has focused on the atmospheric linkages to the tropical Pacific. And one thing I've noticed consistently, the sign of the change in the Southern Ocean is always the same as the Eastern Pacific or the Central Tropical Pacific. Is if one region is cooling, it's likely that the other region is cooling. And this relationship it's found on a variety of timescales. I don't want to say on all timescales, but it certainly extends beyond the interannual ENSO timescale, where you see this strong connection between the Southern Ocean and the tropics. And there's many explanations. So these trends I'm showing here are just recent history, 79 to 2014. And there's many explanations for what's going on in the Southern Ocean. And these processes operate on different timescales, so they're not necessarily mutually exclusive. So there's the delayed warming mechanism that Kyle Armour talks about a lot. There's modes of variability, including ENSO, which I already mentioned, the Southern Angular Mode, and they affect the SSTs through winds and heat fluxes. There's the Antarctic meltwater hypothesis. And then 5 years ago, I went to a number of workshops on the forced response to stratospheric ozone depletion. And so that has an effect on the wind and then on the ocean circulation. And it was never really clear if the models were getting the right response. And sometimes they had different responses depending on the time scale. So they had a quick response and a slow response. And then what I want to talk about briefly today is the negative cloud feedback over the Southern Ocean. So that'll be the next slide. But if the next thing comes up. Yeah, okay. So the last thing for this slide is just a reminder that Antarctic ice cores are literally the Paleo Southern Ocean. So water evaporated off the ocean, got transported to the ice sheet and became ice cores. So I think there's a rich history in these ice cores that's yet to be fully exploited. So I think back when I did my PhD thesis on Antarctic ice cores, I was fairly naive. I just did simple things like averaging the different records together. Now we have much more sophisticated tools like paleo data assimilation. And I think that's a new frontier in this field to get more insight on the history of the Southern Ocean, the history of the SST evolution over the Southern Ocean, especially over the last century or two. There's a lot of work yet to be done with these ice cores and data assimilation. So I kind of pose this question here, since Southern Ocean is a big part of the pattern effect. If models got the SSTs in the Southern Ocean right, and we knew they were getting the right answer for the right reasons, would everything else kind of fall into place? And kind of by everything else, I mean like our understanding of the uncertainty and the pattern effect and climate sensitivity and all of that. So I see the Southern Ocean as kind of a key region for this. There we go. So I wanted to introduce kind of a new aspect of this cooling pattern, or new to me anyway, which is looking at it in the vertical. So this top is kind of what we usually look at, which is the SST pattern. We have this cooling in the polar latitudes and warming in the middle latitudes. But this cooling is actually seen in the vertical dimension as well. So if you look at radiation data or look at the reanalysis, which assimilates these radiation data, then you see that the entire lower polar troposphere has cooled over the last few decades. And this is something that I haven't seen discussed very much. And so I've started to look at it in models to see if models are getting anything like this. And you also see it in ocean data. So this is a cross-section based on the EN4 data set, which you can be kind of skeptical about whether you believe the trends or not. But the trends are consistent with the mixed layer cooling in this region right beneath where the troposphere is cooling. So I started looking for this in our coupled and uncoupled model experiments. So yeah, left one labeled lens, that's from the CSM1 large ensemble. And you see a minimum in zonal mean cooling at about 60 south. Otherwise, the rest of the troposphere is warming pretty strongly. In our prescribed SST run, which is GOGA, which is basically the AMIP experiment, you see like a tiny bit of cooling. You basically see no trend in that region around 60 south. And then on the left there, I have Southern Ocean pacemaker. That's from Sally Zhang's work. And even in that experiment where the SSTs are nudged to the observed, we still don't get a cooling. We get basically no trend there. So I'd be interested in anyone who's done any kind of relevant experiment, just looking at Ed Blanchard Wigglesworth, all right, experiments. So if there's a wind nudging experiment, we could kind of add to this family of runs. But so far, I haven't seen any CSM run that reproduces this lower tropospheric cooling. And so my hunch is that this could be maybe an underestimation of the negative cloud feedback. And so if we look at cloud locking experiments, these aren't for the same time period. These are from double CO2 runs. On the left, what you see there is if the clouds are locked and there's no cloud feedbacks, then there's a really strong warming in this region. But if you turn on the cloud feedbacks, then you do get this minimum in warming. And finally, one experiment that Jen K did was to brighten the Southern Ocean clouds. So if you brighten the clouds, you have more radiation reflected to space, less at the surface, and then you can kind of reproduce this lower tropospheric cooling. So that's kind of a hunch that models may be underestimating.
Can you wrap up soon?
Yeah, I'm pretty much done now. So models may be underestimating this negative feedback and overestimating the positive feedback. So I'll quit now, hand the stage over to the next person.
Hi, everyone.
Thanks, David. Are we taking someone from online next, or should we do Mark first? Yeah?
I think those are Mark's slides, right?
This slide is mine.
Sorry, it's not.
Oh, okay. We'll go ahead and go to Nadir Jivanji online.
Great. Thank you for having me. Thanks to Christy and Maria for an excellent workshop. So as you know, I haven't worked on these topics specifically, but maintain an active interest in it. And so I thought I would give a little bit of a, maybe not quite outsiders, but someone who's at a distance perspective. So in terms of moving the field forward, I think there's a couple of ideas that have come up in the workshop that I found particularly exciting, and that's what I think about, pursuing in terms of making progress. And so related to David's talk, these kind of have a lot to do with the Southern Ocean. Next slide, please. So on the top there, so it felt like we learned something new thinking about the importance of climatological salinity in terms of determining the ocean heat uptake and cloud feedbacks over the Southern Ocean. So that came from Maofeng Liu's poster. And then we learned a bit about a potential component of the ocean heat uptake, which is independent of surface temperature perturbations. And this was in Jonathan Gregory's poster. And that made me wonder about, well, if you have a time-dependent ocean heat uptake efficiency, gamma, which is a consequence of this, what are the implications for the efficacy, epsilon? Does the efficacy still play the same role? Do you still need it to get the pattern effect? And if we're talking about ways to move the field forward, probably updating our nomenclature here, so you don't have two words which are almost the same, but stand for very different things. Confusing graduate students for months on end would probably be a good advance. Next slide, please. I guess I am maybe sort of constitutionally wary of methodologies that that get quite involved, and then you have to figure out how to unpack them. So a couple of examples here, one of which I mentioned when I presented my poster, is that feedback formalisms, which are often used, they require choices. They require a choice of moisture variable. If you're going to do spatially resolved feedbacks, which are of course important for the pattern effect, you have to choose whether you normalize your feedbacks by local or global surface temperature change, and you get very different results depending on these choices. And I think it makes it difficult, it makes it difficult to relate different papers to each other. And then in terms of local versus global, I think the Green's functions approaches that people have been talking about have been great in terms of elucidating the non-local nature of feedbacks, that surface temperature changes in one spot can affect radiation balance in another. But there's an underlying assumption of linearity there, which I'm not sure has been fully addressed. Next slide, please. So Bosong Zhang had a poster where he did something very simple. In the top row, he looked at changes in global mean R and global mean T using the Green's function approach. And in the top row, there's a positive temperature perturbations applied locally. And on the bottom row, there are negative temperature perturbations applied locally, and then the sign is flipped. And if this, if the top of atmosphere radiation, if these variables were linear in the surface temperature field, then you'd expect these maps to basically look the same, but they don't, and you can just see that by eye. So that indicates some nonlinearity. And if you think about how tropical convection works, and I'm citing a very nice paper by Yi Zhang and Stefan Fugelstáler over there on the right, which sort of encapsulates this so-called quasi-equilibrium weak temperature gradient picture for tropical convection. And those words, don't conjure up anything, then I recommend that you read this paper. But one thing that it shows, and it's just making precise ideas that have been around for a while, one of the implications is that tropical convection actually exhibits a well-understood threshold behavior. And you can see that in this plot in the lower right, which shows tropical rainfall distribution as a function of the subcloud MSE, and it's very narrowly peaked and falls off quite rapidly below this threshold. And any system which has threshold behavior is inherently nonlinear. And so, so this breakdown of linearity that you see on the left, from this point of view, isn't surprising. And so, I think we should maybe be asking ourselves harder questions about this methodology, and if our assumptions behind it stand up. So that's all I have, and I look forward to the discussion. Thank you.
Great, thank you, Nadir. Okay, up next we have Mark Zelinka.
Hi, everybody. Thanks again to the organizers. This has been great, and I appreciate the opportunity to be on this panel. A lot of what I'm about to say is just kind of questions that are in my head, and a lot of them have actually been posed by previous speakers and in the discussion. So I apologize in advance because a lot of this isn't particularly new, but maybe seeing it again and talking through it again might bring out some new insights. This is a figure that I stole from Christy. And there's many other figures like this in the literature. One that sticks out is from a recent Stefan Fugestaller and Silver's paper, but this one I think is a little bit easier to grasp the meaning right off the bat, is that, not in a single coupled model that we have currently is able to capture these SST gradients that we see in observations. And you can look at this in terms of West Pacific minus tropical mean. You can look at it in kind of like an omega space. You can look at it in like a precipitation weighted SST space, SST sharp. And you get essentially the same conclusion that it's exceedingly rare, if not never happening in models that you get a gradient of the size that we saw in observations. So what does that mean? And I feel like this should be kind of like one of these all hands on deck kind of things that we try to answer this question. Is it that the models are partly, that it is partly forced and that the models have the wrong forcing, thinking maybe aerosols here, or maybe they have the right forcing but the wrong response to forcing, perhaps things like aerosol cloud interactions, but also things like how the ocean responds to forcing. Is it insufficient natural variability? Like, is this distribution shown in orange here of the model, the 534 model runs, is that just too narrow? It's actually supposed to be wider if you had the correct internal variability in the models. And one thing that I think is really interesting in this area that Paulo brought up yesterday is that it could be related to biases in clouds. We know that clouds are biased in models, and perhaps their response to gradients is also wrong, and that doesn't have the right feedback on the gradient, making them stronger or making them more persistent. So that's something definitely worth looking into. And maybe some would say, well, they do get the right patterns if you run enough members. But is that very comforting that it's extremely, extremely rare that you might eventually, if you run enough ensemble members, get one member that gets a gradient of the magnitude that we saw in observations? So this has been brought up before. I just re-raise it because I think it's really important. Oh, and then the follow-on to that is, obviously, should we trust their future warming predictions? And again, this was brought up again earlier, but I'd already made my slides at that point, so sorry to rehash this. But maybe a new perspective is, can we develop some emergent constraints on future warming? This is what we've done in the ECS world, not thinking about delta lambda, but just thinking about lambda and ECS. There's been a proliferation of emergent constraints. Some of these are dubious, but some of them I think are pretty legitimate, especially if you get down to the process level. Can we do something like this for patterns of warming, for future changes in the SSTs? It was already mentioned that out-of-sample tests like paleo tests would be really useful for perhaps ruling out GCMs that just can't do this right. There's another thing that hasn't come up at this meeting very much is, one is emergent constraints. The second one is machine learning, which is something that you hear about all the time now. And it didn't really come up at this meeting, but maybe that's where we need to go in order to disentangle forced and unforced patterns to try to see what we saw in the past, how much of that is forced and how much is unforced. Maybe linear techniques can't really do that for us, and we need to go on to more machine learning type stuff. I think also it's been brought up a few times that like ancillary information, we don't have to just rely on SST. There's other data out there. Some of it goes back even longer. Altimetry data, sea level data, usage of the subsurface information could be potentially useful. We don't have to tether ourselves to SST all the time to learn about forced versus unforced. 1 minute, all right. This keeps coming up too. How are ocean heat uptake and TOA feedbacks related via the pattern effect? I find it interesting that the exact pattern, like this La Nina type pattern, is one that is very favorable for ocean heat uptake. It's also very favorable for clouds to reflect heat out to space. So the exact same pattern that gives you a ocean sucking heat out is the one where the clouds are also saying, no, the heat's got to go out the top, kind of in the same location. how are these related to each other? This has come up a few times, and I think there are some interesting ideas out there for that and trying to reconcile these things or try to relate them to each other via the pattern effect. And then finally, this is one that maybe hasn't come up too much, but I find this to be a conundrum. So coupled models get too much tropical upper tropospheric warming, and that's kind of shown here on the right. The amount of upper tropospheric amplification of temperature in the tropics has for years been shown to be larger in models than in observations. This is a popular skeptic talking point. And some of this is obviously data observational issues, but I think that this fact remains that the models simulate too much upper tropospheric warming in the tropics. And yet, they also do not simulate enough of this east-west gradient. And we know that warming in the West Pacific gives rise to an amplified warming with height. So how is it that the models are getting very homogeneous warming patterns without this large amplification east-west, but yet they're still getting that wrong? It seems inconsistent to me. And so I'd like to raise that as another topic, kind of a conundrum that would be worth discussing. There's probably something very simple there that I'm not seeing. Thank you.
Thanks, Mark. And now we'll go to Pierre's Forster online.
Yes, well, the first thing I want to say is it's fantastic to be at this workshop. There's a lot of intelligent conversation going on, and it's a fantastic workshop, and you probably aren't going to get intelligent conversation from me today. But in fact, it is surprising that when I did prepare my little talk today, I didn't consult with my colleagues, but we are going to bring up a lot of the same considerations. So the first point I thought about as I did listen to the great presentations was that I think if we can begin to really define what we mean by the pattern effect more precisely, particularly about the physical processes, and we begin to talk to from those perspectives, and we've had good talks on looking at the AMOC or looking at the stability, for example, and I think the more we think about the physical processes, the more we'll be able to make substantial progression in our work. Okay, could you go on one slide, please? And the other thought I did as we did talk is that I think perhaps we can't understand it perfectly, but we might be able to set some bounds of some kind on how significant we think the pattern effect is. And this some work by Lawrence Jackson, where what he did was to look at the temperature trend you might get from a persistent historical pattern effect continuing, and then what you might get if there wasn't a pattern effect occurring at all, and you can then think of something in between those extremes, which is the historical pattern effect changing over time. And I think it's interesting to think about perhaps what actually are the extremes on what might occur. So that's something interesting to think about. Could you get on my slide, please? Yeah. I think as we try and work out what's going on, it's very important to remember those great talks from the first day of the workshop, where we have to be very careful about the observation we are working with, and we have to think about ourselves. What are the uncertainties, and perhaps the pattern effect doesn't actually, perhaps it doesn't exist particularly, or perhaps it's not really that significant. So I think we have to bear that in mind with our kind of work. Could you get on one slide, please? Yeah. Uh, 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 and of course, what we're doing here for the workshop is really trying to think of some quite cool experiments. And it's interesting that some of the points that I picked up were exactly what David and Mark picked up, and what Keith is going to say after me is, hell, perhaps. They're things like, perhaps we can have more luck, perhaps, by trying to look what's happening in the Southern Ocean, and perhaps we can look at the response to radiative forcing in a bit more detail. I don't think that's been investigated in much of other particular things as well. And like a lot of other people, I'm very excited by the use of screened functions to work out what is going on. But I think we have to be very careful to remember that the system is coupled and it is quite interdisciplinary. So I think the workshop has really brought all of us together in this interdisciplinary type of way to work out what is going on. So I just really think we should capitalize on that fantastic collaboration. Yeah, and that's the end of my talk, really. So over to Peter that will give you the answers.
Thanks, Piers. Last but not least, we have Geeta Prasad, who's online.
Perfect. Okay, so thank you very much to Maria and Christy for such a phenomenal workshop. I know I've learned a great deal, although I was starting from near zero, so that's maybe not saying much. But most of my comments today come from the perspective of someone who thinks about these short-lived, highly heterogeneous climate forcings and their impact on climate over relatively short time scales, so in the context of near-term climate change. And I'm here partly because I think, or rather Maria told me I should think, that we might be talking about some of the same things in both communities, and I wonder what we can learn from each other. So my plan here is to sort of ask a series of naive or maybe devil's advocate questions with the hope that answering them for me might help people who know more about the pattern effect think about ways forward in a slightly different way. So the first question that I've been chewing on during this conference is the SST pattern the only thing that matters for a pattern effect on decadal to multi-decadal timescales? And here I'm thinking, I mean, the pattern effect sort of broadly construed as any time evolution in the feedback parameter that we think might have something to do with spatial patterns. So one thing that comes to mind there and that we've had some discussion about is the potential role of land surface temperatures. We've talked about maybe one of the reasons that we focus on SST is that it's computationally harder to prescribe land temperature. But is that the only reason? You know, we think land surface responds more quickly, so maybe it's less important in the long term. But if we're thinking about the historical pattern effect, the forcing is constantly evolving, so the land surface temperature is also constantly evolving. So what role does that play? And then, of course, the thing I think about a lot is what about the spatial pattern of the anthropogenic radiative forcing and the associated atmospheric adjustments? So here again, I'm just showing these results from my 2018 paper that I talked about a little bit in the lightning talk, where we found that if you move a given aerosol emission around between sort of different national scale regions, you get substantially different forcing efficacy. And it just so happens that historical aerosol hotspots like Europe and North America have a stronger efficacy than current and projected hotspots like India or East Africa. And in the paper, we used radiative kernels to tie that efficacy difference back to differences in the cloud and the ice albedo feedback strength that you get from a given forcing pattern from a given regional emission. And I think one question, of course, is how regional, you know, how heterogeneous does the forcing have to be for you to get these strong efficacy effects? But you might imagine this mapping onto a time evolution of forcing efficacy from aerosol forcing, which is something that I'm currently thinking a lot about. But then in addition to the anthropogenic forcing, what about patterns of heterogeneous natural forcings that might be correlated with large-scale shifts in the climate system? So I'm thinking about things like land cover change associated with vegetation regime shifts that could act as an evolving internal spatial pattern, changes in desert dust patterns, wildfire emission patterns and locations, ocean DMS from phytoplankton as patterns of primary productivity hotspots shift. So what are these other time evolving spatial patterns in the climate system that could contribute to the time evolution of the feedback parameter? And then if we can go to the next slide, this is really my devil's advocate question. And this is something that I've thought about since PhD days at GFDL. Sort of what is the utility of understanding the purely CO2 driven feedbacks? What is the utility of a 2x CO2, 4x CO2 sort of framework? What is the utility of equilibrium climate sensitivity at all, right? Particularly if we think the feedbacks behave differently in response to other forcings, and we're never going to be living in a CO2 only world. So, I mean, maybe a very uncharitable way of framing this is that we often seem to think about trying to understand this present day complex historical pattern effect in order to constrain what's happening in the equilibrium response to CO2 forcing. So sort of like what's happening in this figure I'm showing that we've seen multiple versions of over the course of the workshop. Or to figure out how much the past can tell us about this long-term equilibrated response. But in reality, certainly on modern climate change timescales, multiple forcings are varying in tandem, and they will be for the foreseeable future. Even if we're thinking on CO2 timescales, and you can argue that CO2 is the big hammer there, the CO2 forcing is still happening on a background of all other sorts of Earth system changes that we have reason to think are important. So Maria talked on day one about the fact that we can care about the pattern effect even if we don't care about ECS and just care about near-term climate projections, because we do need to explain this discrepancy between the historical and the forced warming. But in that context, I would encourage us to think carefully about forcings besides CO2, of course, aerosols, I need the shirt, but also land use changes and other things that we might imagine, which are much less well constrained in the models, not just in terms of the model response, but also just the basic historical inputs to the models. I think if we really sat back and think about it, we might realize that they're mostly trash for things like aerosol. Right, but those can also help contribute to this discrepancy. Thanks. And so just the last thought on this, granted, all of these other things are going to be smaller in the global mean than CO2, right? And I think this is why we think about CO2 so much. But we've heard a couple times now that it's not the pattern of absolute SST so much as it is the pattern of anomalies from the global mean that creates this pattern effect, right? So in that sense, the relatively low importance of some of these really heterogeneous natural or anthropogenic forcings in the global mean might not reflect the size of their importance for the pattern effect or for feedback strength. So with that, I'll be really interested to be proven wrong on all of this. Thanks.
All right, thank you, Geeta. So we'll go ahead and start off with just if anyone on the panel, any of the panelists have questions for each other. If anyone wants to take a stab at Geeta's few questions at the end of her presentation.
Hello? Yes. Okay. This is just a quick follow-up for Geeta. Are those regional aerosol experiments including aerosol indirect effects, or is that straight direct effect that you're analyzing there?
It's including direct and indirect effects, yeah.
All right, thanks.
Cool. If there are no other questions from the panelists to each other, we'll go ahead and open up questions to the audience. No one has filed up to the microphone yet. All right, we got a question from Sebastian.
Okay, I'll start then.
Piers, you can go ahead.
Okay, what I'm gonna ask Geeta, I'm not sure if the aerosol changes to push the right way for the historical time today. I mean, if you do have aerosol recovery and you have the aerosol changes with the high efficacy term, I mean, yeah, it's the time. I'm not even convinced they go in the direction you really can want them to.
Yeah, no, I think you're right. And I think, so, the regional results I have would suggest that the spatial pattern of aerosol emissions is transitioning towards a lower efficacy pattern, not a higher efficacy pattern. But of course, mine is only one study that suggests that there might be this signal, and I think it would be really valuable to have a MIP of this kind of thing. And we, in some sense, have something like that for PDR MIP, but it's much larger for things. And so if you think about linearity, we also have to think about linearity in this context, right? Like what happens when you have all of these regional perturbations happening simultaneously? And so one of the things that I'm thinking about is, you know, I think we can use the existing DAMIP and AMIP experiments to look at what the actual historical evolution of aerosol efficacy has been, and potentially constrain some of these questions about whether this regional picture actually manifests at the global scale. And then I think it's interesting too, like what is going to happen in the future, right? We have very little constraint on what's happening going to happen at the regional scale with aerosols in the future.
Great. Okay, we'll go ahead and take a question in the audience from Sebastian. Go ahead. And if you could introduce yourself and your affiliation. Thanks.
Okay. Sebastian Walensky from MCAR. I had some thoughts on what you showed, Mark. The figure that I think comes from Christie originally, which shows this distribution of all of the models and observations sitting on one edge, or maybe even outside of that distribution. And Malte posted a very similar figure to the Slack for the Atlantic. And my thought was, how do we interpret that? I mean, you offered the interpretation that it's exceedingly unlikely that the models are right, observations sit on the edge of that distribution. But we are really putting two types of uncertainties together there. One is some of the models will be systematically wrong, and then there's internal variability. So I think one way to do that differently would be to take large ensembles, and for each large ensemble, basically plot that. Take one that has a kind of mean force response that lies reasonably close to observations, and then we wouldn't need huge internal variability, but we could try to quantify how much internal variability do we need to include observations. And then we could follow up with what you suggested to try and validate internal variability in such a model. So to end on a question maybe is, how do we interpret these types of figures?
I think your point is well taken. Yeah, I think that would be one way of doing it. Would be in the large ensemble approach. And just the first thing that comes to my mind is some work that Steve Pochedli did on looking in the large ensemble. And there you will occasionally find a member, and he was not looking at east-west gradient, but it was more of like a Nino 3.4 trend. And you know, rarely do the members capture that even, but some of them do, and they actually look quite similar to observations even in the subsurface. So I think you can probably play those kinds of games to try to find members that look right and try to understand why that is. Yeah, you want to follow up?
If I can just add a thought on that. In this, you would say that since the observations are so close to the edge, it's really unlikely, but you might still find one or two members. But if you have a large ensemble where you have, say, 10% of the members include this observed trend, then you wouldn't say anymore it's so unlikely that it's probably not real, but it's just a very unlikely trend that we observed. So it would kind of shift the probabilities a bit.
Right.
Just a quick comment to say that my poster has this figure for different large ensembles separately, and I'll post it.
Rob, can you introduce yourself really quickly? Sorry.
Rob England-Wells, University of Washington. Figure just like this, but separately for different large ensembles. I'll post it in Slack.
Go ahead.
I can also just quick follow up just related to this. So Malte Stücker, University of Hawaii. So yeah, I posted a figure in the Slack, and it's actually the Atlantic minus Eastern Pacific gradient that's shown there, but it's similar distribution. And our hypothesis back then was that, and we did this with some tests, that actually the SST climatology bias in the Atlantic prevents coupling between the Atlantic and the Pacific via the Walker cell, because it's biased, because the tropical Atlantic is too cold in the models. And if we correct for that, then actually this linkage is much better. So there the hypothesis is that due to this reduced linkage between the tropical basins, actually we have low biased internal variability, and also forced, if like there's even force changes in the Atlantic, they cannot communicate with the other basins. So that limits. That's why I like the idea of going back to flux correction to get a good model that can simulate this connection and do long controls, see where this distribution is, if we can actually widen it, or if actually the observations move more there. So that's a testable hypothesis. I think it's worth exploring.
Yeah, I wonder if, as part of the record of the meeting, if some of these ideas of things to do going forward, like a flux, like going back to flux correction, should be noted. To which I would add, it came up earlier too, that we're always lamenting that the AMIP ends 6 years ago or something like that, and we just missed the last thing that we wanted to see, or we missed COVID entirely, and we missed the recent El Nino. How hard would it be for modeling groups to not be so tethered to the CMIP cycle, but like every so often extend their AMIP runs as the new SST data sets come in and all the boundary conditions come in, just to have that be kind of an updated data set that we can tap into more regularly through time. I mean, is that something that this community might want to advocate for more strongly to the CMIP community, as maybe like a flux corrected MIP or AMIP run more regularly? And another one that occurs to me would be the running multiple AMIPs, not just with the default PCMDI AMIP SST database, but or SST boundary conditions, but with some of these other SST data sets that we've discussed that are subtly different, but in important ways. Is that something that we should maybe be advocating more strongly for in CMIP or outside of CMIP?
Christy, you have something?
One comment on that. If all of the things that you think we should advocate for, you should explicitly bring up in the last breakout discussion and on the slides for moving forward. And yes, all of those things that as a group we agree on are important going forward will go into a workshop report that will be both published and sent to funding agencies. So yes, all of the things that such suggestions are very good, and they will be recorded and passed on to whoever wants to read those reports.
Thanks. Clara, did you have a comment or question? I saw you.
Clara Desser NCAR, just a small comment that the part of the CSM Climate Variability Working Group, we keep our AMIP runs up to date, and they're available to anybody. And we also keep these tropical Pacific pacemaker runs, so a more coupled system up to date. So this is all available, and happy to point people to the data.
Oh, cool, thank you.
Thanks. Vince, you can go ahead.
Hi, Vince Cooper, University of Washington. So Mark showed a plot that had kind of model bias and too much tropical upper troposphere warming, possibly being connected to the east-west gradient. It kind of got me thinking about clear sky radiative cooling. I guess I was just wondering whether through the kind of radiator fin mechanism, whether what you're kind of getting at, Mark, is the possibility that there might be like clear sky radiative cooling biases that could be kind of downstream or I guess upstream connected to the kind of 2-week east-west gradient. Is that kind of what you were thinking of when you brought that up? And maybe it's something that Nader's thought about as well.
I was not thinking about that. I was just trying to reconcile in my mind why, if models fail to get a sharp east-west gradient, why they simultaneously seem to get too much upper tropospheric amplification, because warming that's concentrated in tropical ascent regions should give you a very much vertically amplified warming pattern versus, and that's, observations have shown warming that's concentrated in the west and models have not, coupled models. And yet the coupled models they overdo the upper tropospheric amplification. So it seems backwards to me. So that was more what I was highlighting. But clear sky radiative cooling part, maybe Nother has some thoughts on.
Perhaps I'm going to come in and interrupt here, but sure that could be, could you get too much tropical troposphere upper warming in the eastern Atlantic, perhaps, which you don't necessarily observe, perhaps, as well. So anyway.
Yeah, I could jump in here. Mark, yeah, I think that's a great tension that or it's great that you point out that tension in this plot on the right. And I mean, one potential resolution is the way models are parameterizing entrainment and convection and how that sets the lapse rate. And if the convection is not dilute enough, then you get this pure undilute adiabatic warming, whereas real convection is more dilute. That'd be one hypothesis to look at, but if that's, and there's been a little work on that. Osamu Miyawaki has a nice paper on that. But if that's not it, then yeah, it seems like a puzzle, worth looking into, and that we would learn something important because the tension that you point out is pretty clear. In regards to the question about clear sky OLR, I'm not sure how that relates, or clear sky radiative cooling. I'd have to think a bit about how that relates to this tension that Mark is pointing out. One thing I can say is that Yizhang wrote another paper with Stefan and I where we looked at the clear sky OLR in GCMs and tried to tie it to simpler models, single column models. But one thing we found, which we didn't highlight, was that there's actually a surprising amount of spread in just the base state clear sky OLR from, this was CMIP 5 GCMs, I mean, several watts per meter squared, much more than you would, would be deemed permissible for the all sky OLR. And so that there may be some uncertainties there that as a community we haven't zeroed in on.
Thanks. Do we have any questions online first?
Yes, we have a question from Brian Rose. Was it Nader that mentioned ocean heat uptake efficiency versus efficacy creates terminological confusion? I wonder if anyone in this workshop has bright ideas for new and improved terminology.
I gave it a moment's thought after making that slide, and nothing obvious struck me, but it's worth putting some brain power in.
Okay, I guess we'll move on to the next question. Kyle, do you have a question, or go ahead?
Steve Puchadley at LNL. I was just going to comment on this problem. There's lots of subtly different problems with tropospheric warming. This problem, I think, has been resolved. It was a data issue. So if you extend this plot to 2020, the red and the blue dot, which are observations, are now up where the models are at. The upper troposphere warms about 1.2 times faster than the lower troposphere. But there's other related problems, which I think a lot of people have talked about, where models, the absolute rate of tropical tropospheric warming is faster than the observation. So not the relative surface to troposphere warming, but the absolute warming. And it's confusing because in observations, the West Pacific is warming really fast, and we think that the troposphere should be sensitive to that. And I think part of the resolution to this conundrum is that the observations in the Western Pacific are not really warming faster than the models. And at the same time, the East Pacific is cooling. And so you shouldn't necessarily expect the observations to warm as fast or faster than the models, even though we have this strong gradient. So yeah, there's a lot of nuance here, but
yeah, thanks. That's helpful. So the tropical mean warming also seems relevant. It's not all pattern. The rate of tropical mean warming is relevant too.
Yeah, and observations warm less than the tropical mean. And another factor is the SST data sets have really big uncertainties. I think the tropical surface trends differ by maybe 50%. So it's not like all the data sets agree on how much or how quickly the surface is warming.
Yeah, thanks, Steve.
Great, Kyle, you can go ahead.
Okay, I want to come back to this point that I think both Piers and Mark made about the kind of coupling between the ocean and the atmosphere. I think this is a really important question that's kind of wide open right now about when you have a pattern effect that translates to radiation, how does that same pattern effect translate to ocean heat uptake, and how do you reconcile those two things? But I've been thinking about this lately, and I think it's been framed in the workshop so far as if there's a compensation between like an ocean heat uptake efficiency and radiation, such that when you have less radiation to space, you should expect less heat uptake by the ocean, which has to be true in terms of a global energy conservation. But when you start thinking about redistribution within the ocean, it's not so obvious. So to give you just two examples. So the hiatus period was a period of accelerated trade winds, which basically enhances subtropical cells and enhances deep ocean heat uptake, which cools the surface. And that was kind of the explanation for a slowdown in global warming. But that same spatial pattern of SSTs reduces radiation to space. It's a very negative feedback. So both lambda and kappa, that is the radiation feedback plus the heat uptake efficiency, work in the same direction to slow down global warming. And then another example would be Yue's work on Southern Ocean hosing, where she's diagnosed feedbacks and heat uptake efficiency. Those also work in the same direction to slow down global warming. So I think this is a wide open area, but it's not obvious to me that there should be compensation. I think they often work in the same direction, amplifying each other. So I'll just throw that out there. I'd love to hear examples where they could compensate. I actually can't think of many. Maybe Emily could speak to that. I think she might have some work on that also. But anyway, I'll open that up to what you might have been thinking about in terms of compensation. Yeah, thanks.
Yeah, and we were discussing this in the breakout too, that the timescales probably matter as well. Like the atmosphere very quickly responds to the SSTs and it causes a TOA imbalance, a TOA flux anomaly. But the ocean heat uptake probably takes a bit of time, and so the pathways are a little bit unclear exactly how that heat is getting redistributed around. But yeah, it's a good question.
And I would completely agree on the time scale, just because perhaps things have to compensate on some relatively longer time, but I don't think they have to at all. And if you go back to some of the thoughts of the interannual variability that was showed the first day, I mean, I think you can have a whole decade quite easily where they aren't compensating. So I think it's interesting to think about what are the different physical processes that cause that.
Cool, thanks. Do we have another question online, or Chrissy?
So this is for Nader. It's a really nice point that this asymmetry in convection, due to it being a threshold process, creates a nonlinearity which sort of messes up the nice linear Green's function framework. But that seems like it's a problem that applies to some of the other frameworks as well. Like if you move away from geographic space into SST sharp and tropical average SST, or in the Cheppy and Gregory framework of temperature and stability, those don't really get around that problem, even though they're not Green's functions. So do you have any thought for what would a framework look like that would easily incorporate this kind of nonlinearity?
That's a good question, and I asked myself that, and no, I didn't come up with a good answer. But I think you're right that whether your temperature field is in geographic space or in percentile space, that's right. I think you bump up against this problem either way.
Cool.
But perhaps Mark can explain why he thinks that machine learning could be something we could do to try and understand this. Just because, I mean, I thought that machine learning wasn't much good at telling you things you didn't already understand. But perhaps you can tell me why I'm not right there.
I'm definitely not the right person to tell you why. I was hoping that there'd be some other machine learning person who would be excited to explain how that would be helpful. But maybe in the case where linear things like EOFs and stuff are not sufficient to explain what's going on, maybe relaxing some of the assumptions that are in linear or those sorts of approaches would be helpful in discriminating between forced and unforced. if anybody's here that's working in that area, now would be a good time to chime in. But I was throwing that out there as something that maybe we should be thinking about without any real ideas on my own.
Claire, you go ahead.
Yeah, I just wanted to bring in a thought on Christie's question and Nadir. In the ENSO community, to get around this asymmetry between El Nino and La Nina, which I think has similar threshold behavior, if you will. There's something called the ENSO longitude index, and it's the longitude of the precipitation maximum that occurs. And that's very linear with respect to the position or the centroid of the SST anomalies in the tropical Pacific. So it kind of resolves this Central Pacific versus Eastern Pacific El Nino events and the difference in the spatial patterns between La Nina and El Nino. So perhaps for this community on the pattern effect, we could tap into that framework, and it might be very useful.
Okay, great. Thank you, everyone. I think now that it's 2 o'clock, we're going to close our panel discussion. Let's thank the panelists really quickly.